Welcome back, people. Let's begin. So, I've done a couple of changes since we last saw each other. What I've done is I've trained a bunch of new models. Particularly, I've actually changed the learning rate scheduler that I was using. Earlier, I was trying to use the multi-step LR or one cycle LR, but it wasn't giving me good results. The thing with transformers is that they work very well if they have very small learning rates. So what I did is I went back to the drawing board. I used the NOAM scheme that was used by the Vaswani in the original Transformers paper. Now what that does is you have a linear warm-up for some steps, and then post that you have an exponential decay. The other algorithm that I used was the one that used cosine decay, and this step used about 7%. You see the gray one, it used about 7% of the data set was used as for warm-up. 7% of total steps was used as warm-up. In the cosine decay, I used 25%, 14% of the data set as warm-up tokens. And so you can see it actually performed much better. The loss finally hit below 0.8. But if I just show it to you on a larger scale, it doesn't really matter as much because it's actually going from 0.85 to a little bit about 0.75, which means that the value is still, it just reduced by 1. We would like it to go till 0.3 or something like that, while the total loss finally goes to 3.63. So what we're going to do is we're going to stop training this model. It's still running, and yeah, let's use the cosine annealing. Yeah, just kill -9205. What I've done is I've added another scheduler, which is warm constant. So this is from transformers. Let's show it to you. So these are all the different schedulers that you can use. T5 uses this particular scheduler, which means that one here is the multiplication value to the learning rate. Yeah. So what I've added is I've simply ported a couple of them. I put them here, and I'm now using this scheduler. Another thing that I've added is now we initialize the weights in a consistent way. So you can see the moment I press train, it actually the first thing it does before scheduling the optimizer, making the optimizer, is that it applies the init weight functions, which creates a much better, a much better initialization for value than the default one. And finally I ported the optimizer, the AdamW optimizer from Karpathy. So from Karpathy/MenGPT, this is a learning rate decaying optimizer. What this does is that at each step it reduces the weight value by learning rate times whatever is your weight decay. Here it is 0.1. So it reduces. So the entire objective of weight decay is the weight of all these parameters. So the parameter value should eventually start hitting 0. That's the idea here. And so we've stopped this training. Let's actually just push this code to cloud, and we'll begin again. Git status, git diff. See the percentage and total steps upon GS. Yeah, I mean, yeah, none of these are useful. I've already ported it here, and we'll need to add it here. GST git add this, git commit add warm constant. I don't know what's the better name for this. What should we call it? get constant schedule with warm up. Yeah, warm constant, much better. Plus typos. This again is going to be a fairly long stream because I want to study a little bit more on the exact learning process. So what you're going to do is you're going to create simple Testbench code and also run that. Okay, this is done. We'll probably initialize on the terminal. Alright, models are done till A8. So yeah, so what's going to happen in this particular new run is we're going to take the learning rate till which is 0.04, and we're going to keep it constant at 0.04 for the entire run. Now why I'm doing that is that, see, at 0.04 you see it learns very efficiently while the learning rate keeps increasing at 0.4. It reaches to 0.4, and the moment learning rate starts to decrease, which happens at the top, the eventual momentum, because of the momentum, it does not learn very well then. Not exactly learn very well, the update value starts to decrease. Yeah, that's a better way to say it. What you're going to do is python train.py --name name is A9, and let's start. Syncing run Wise Fire 19. That's a sweet name. So we're going to turn off all these other runs. It's no longer needed. This is the best run we had till now, and we are going to consider this only. 0.8 works well. Var's argument must have ticked attribute. Okay, so that didn't work. What we're trying to do is we're trying to initialize a better was. Let's close these values because these are probably old code. Jupyter does not update the file if it is already open, which is super annoying. Yeah, vars object. Yeah. So what I've done here is we only need to log two things on weights and biases, which is what is the warm up percentage and what is the scheduler. Is because what we're going to do is we're going to play with these values, and these are the values that when we start sweeping the models, this is what we're going to use. So yeah, we're going to sweep the models. We're going to study a little bit more on the learning thing. Why is it so that because of the loss of policy, because of the large loss of policy and small loss of value, policy is learned faster? That's not true, by the way, but we'll see if that is actually the case. Okay. We should probably open another terminal here. Yeah, let's just keep this thing here. Okay, so this one is wobbly music 20. Again, integer division or modulo by 0. No worries. Alright. File not found model.py. Alright. So we delete more wobbly music, delete this run. We can do what we can do later. So what is the name you're giving to run number 21? Serene Galaxy. Nice. Okay, so using NumPy zips. See, it loads so much faster now. You're using very high percentage of GPU now. Like the GPU memory allocation is average is about 95%. Say see 92 and 99, it gives you like 95. So we have pretty decent allocation now. Can possibly pump it up like 1 or 2 batches, but you know why? What's really the point here? Okay, let's see how this model works. This, you know, it'll take another 2 to 3 hours to actually show us if it is learning something in a better way, because a large portion of it is going to follow the dual set energy run 18 red run, and we should probably change the color to blue so it's much more clear. Yeah, that's the blue. Perfect. More. It's not updating or what? Auto refresh is on. It should be updating with some value at least. Oh yeah, it is updating, but because of these graphs it's going to take a lot of time, so let's just let it try. Okay, the next thing we're going to do is we're going to run a lot of dummy models locally, particularly for regression and classification. We'll study a little bit more about different loss functions, and we'll see if this is actually the case. The problem here is that the loss is not decreasing as quickly as it should, and probably the reason is particularly for value, and probably the reason is that the loss value is 0.8, whereas the loss coming from the model, the policy, is actually closer to, so at the end you have 0.77 loss here, the end you have 0.28 loss, which means it's the loss coming from policy is 4 times the loss. So we'll read a little bit more about mixing different model, mixing what should we say, 7% of steps. Okay, it should be 14, but okay, that's fine. And then we'll read more on the sweep, what exactly is sweep, and how can you actually utilize sweeps. Sweet. Okay, alright, let's begin. Mixing losses neural networks. Scholarly articles. But what are different loss functions used as optimizers? Optimizing the mixing proportion of neural network based on genetic something. Let's see what we have. Seriously? It's crazy, man. What kind of work people are doing with this thing? Pretty impressive. Alright. Multiple outputs and multiple losses. category branch, and you have a color branch. A couple of weeks ago, we discussed how to perform multi-label classification using Keras and deep learning. Today, we are going to discuss more advanced technique called multi-output classification. I need any of this. This is too big, man. Nobody works like this. You should have pooling. Pooling works way better. Sorry, not pooling. Having a residual block and at top having simple heads. Useless. Mixing loss functions. Multiple loss functions. Maybe something in these things. Multi-loss dual output convolution. Is it the same article that we just saw? How do people get away with this kind of poor work? Loss regularizing deep neural networks, multimodal dimensional emotion recognition. Task learning in deep neural networks, large scale multi-label text classification, multi-object tracking. My god. You know what? Let's not bitch on people. That's not a good thing. Soft parameter sharing. Hard parameter sharing. We also need to see how we can implement what do you call it? L2 regularization on parameters. This is again. Okay. This is for JPEG deblocking approaches. Mix outperforms both L1 and L2 in uniform regions as well as on ringing artifacts at high gradients. No. None of this actually helps us. What I need to know is it true that if I have different learning functions, different loss functions, how much does it affect us? Efficient backpropagation. This is a good book. I'm going to read this whole book. It's going to take me a couple of months, but let's just do it. What? Man, this is when you're actually live streaming. This kind of thing helps. Somebody who's watching this might have faced a similar problem. Might suggest a very good solution for it. You know what? It's a coding stream. Let's code a little bit. So this is the cosine decay thing. This is the exponential. In all these cases, the best thing I've done is I've actually used a lambda LR, and all it has to do, it takes in you just have to send it one function that takes in the current epoch and returns the final value. So let's begin with the test bench. Okay. So for what we are trying to do in this test bench is simple. We want to analyze the effects of regression and classification. What happens if two different models, a single model has to predict two classification tasks, a model has to predict one classification, one regression task. If it only has to predict a regression task, only a classification task, like having two different neural networks, one for regression, one for classification, things like that. This thing is addictive. Actually training a neural network, you just want to keep staring at the tensor boards. You know what? We're not going to do this. We're not going to stare at it. Okay, so the first thing we need to do is we need a very, very simple test bench. A very small data sets for not logistic regression, for regression. Dev create data sets. So the first data set, we are going to define whether it has regression is equal to false, which is whether this has a regression task or this has a classification task. So if R and C, what we need to do is we are going to create a simple data set, and we also need to know the n, which is the number of samples. So if R and C pass like our data set, LF R pass simple regression, LFC pass simple classification, and else there's nothing else. Okay, so for classification, I know what you need to do is we are going to use something very simple. People go and subscribe to this thing, star these things, follow this page. This is my new, not exactly a startup, but this is my new project, and I'll be working full time on this thing. Alright. So this thing almost gives me a dataset. I don't need that. Instead, I just need the URL. Alright. URL this. Then all we have to do is we fetch the URL. Fetching function is unique to tinygrad. Anyways, cars, this thing, this, except that there is no self. We're going to do hardcode max length to say 10 because we don't want anything more than that. And data is, yeah, data is so much better. Data is maybe going to be, let's just find the fetch function first, which is tinygrad.utils. And fetch. Okay. And let's just test it. Out is equal to this times, sorry, argument is the URL, fetching this thing. And if I do out 1 to 10 binary first city, so then I have to convert this, I have to decode it to UTF-8, which I do here, and then it makes much more sense. I don't need any of this. Open fetch, yeah. Makes much more sense now. This is going to be my data, and my final data is actually stoi x for x in data, and let the max len be like max len cross n. This is the number of samples I need, and I'm going to convert this to np.array just for simplicity. Max len should be 11, 10 plus 1 because you're training this thing, and return data. Alright, let's see. Data is equal to create data sets, n is equal to 10, c is equal to true. Data, okay, perfect. Dot reshape -1 cross max len. This thing has no attribute. Okay, perfect. And we also wanted to return not just data, but what's this, man? This is vocab. Vocab, and vocab. This thing, and this thing gives me the inverse vocab. Perfect. You know what, the thing we're going to do is we're going to lower this whole thing so the vocab size is actually even more smaller. So now your vocabulary is just 38 tokens, which is perfect. This is good enough. For regression, what we need is, for regression, what we can do is we can create certain functions and tell transformer to actually return no. So our functions is going to be a sine function, sine plus noise. So your data is, let's create an embedding. This way we'll always be fixed towards what we want. np.randn, np.random.randn, and the size we're going to give it is, our vocab size is 38 fixed. This way let's just hard code a couple of things. Vocab is equal to 38. So vocab size is 38 and the target dimension is 3. I think this is good enough. Perfect. And your data sequence is going to be no, we don't create embedding here. Our input sequence, it is going to be np.linear linspace np.range 10 np has no range, arrange, sorry, perfect, np.arrange 10, and our input sequence should be np.linspace something like 0, stop is 10 cross np.pi, and this is 10. Perfect. Okay, perfect. So our input sequence is going to be this thing, which is input is this, but actual input is going to be used as this thing. No, this is input, this will be x, len input p.pi, y is equal to np.sine of x, np.arrange, and what we need to do is we need to patch these things together. So to list cross 4 gives you this thing. Okay, perfect. Dot to list cross n, and we'll hard code another thing, which is max len is equal to 10. Alright, perfect. Max len is equal to 10. Vocab size is 38. We don't really need that here. Now arrange is actually going to be vocab size, and length of input cross n. Yeah, that's fine. And now we simply convert this to an array. Input till whatever is len input modulo No, not modulo. What do we do here? Oh man, I'm so stupid. Once I write something, I pretty much forget it. Okay. Up to negative of this thing. Makes sense. So this is our input dot reshape -1 cross max length +1. Because we're going to take the losses, and we simply return input and y. Okay, let's see what happens now. We have x and we have y. Here r is equal to true. Cannot reshape an array of size 5 to shape 11. Okay, so what exactly is our input? It's a pretty big sequence. What is this thing? What? Oh shit. Oh shit. Did we do a mistake in creating a data set? Okay. So this is your x and this is your y. So this is some sort of a function you have. No. This is np dot pi cross input as array. Okay. So now we have the regression dataset ready, and finally we need a dataset that has both regression and classification. So this is basically going to be a merger of these two things that we have built here. How is it training? How is it training? It's training worse than the other two models. Did we do a mistake? You know what, the worst thing I did, I didn't even plot what this thing looks like. La Lambda. Num warm-up steps is, we fucked up, didn't we? Train.fire is still using the norm DK. This is annoying, man. You have 7454 control Z kill -9 what was it, 7454. Okay, train, this is to delete this run. So what a waste of time. This is what we want. Warm up constant. We just wasted 30 minutes. This silly bug. Sunny Eon, now you are assigned a color blue. I messed up the epoch code. That should be fine. So now it's going to go till here and it's going to be constant. So till this piece it's going to give us the same behavior, which is approximately 1 to 1.5 hours into the training. Oh, and then we have the wait, we didn't fix this bug, man. I should no, this isn't fixed. This is just warm up. So you see it goes till this particular value and then it stays there. Perfect. Cool. So we should be seeing the same behavior here as well now. Yeah, now you have these two things combined, and so what we are going to do in this case is we are going to take all this information, say that this actually is our data. So this is going to be our input, and against each input we want to calculate what is going to be the sign function. So data x is equal to data times np dot pi, y is equal to np dot sine x, and returns data and y. Shimpa, 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 shimpa. And the second thing is, we'll consider this particular case. What? Oh, these are not. Y is equal to y dot reshape minus 1 max length plus 1. Cannot reshape an array size 380. Alright, cool. So now we have all three datasets ready. Perfect. Now what we need to do is we need to create a simple model. So should we just import our model only? This way we can actually test this thing much better. Yeah, let's just do that. We're going to import our models. Yeah, that's right. That's right. Alright. So we import our models. Currently logged in as Yash Ponde. No. This one. We don't want to use this thing locally. Here it does say what is WNB offline. Turn off syncing. Okay. We should put this thing here. Top. Alright, now you have all these things, and so now the first thing we need to do is we need to create our models, which is, this is how we are going to do it. We're simply going to copy paste this. Vocab size is vocab, and positions is maxlen, NC and TX is maxlen, and embedding is up to you. Let's just keep it at 2, and layer is 1 and head is 1. And that's it. And if you want to see the number of parameters that are in this model, yeah, see, it actually copies the very similar path. It's actually low. Interesting. Yeah, so where is this thing? Train.py, we go here, model size is this, take it here, we're going to say this, model size is 229 parameters, which is, it should be fine. For classification, we do have a super tiny data set. What we can do is, let it be. Let's just play with this model first and then we'll see what happens. Okay. So if I pass model and let's just test with the regression data set first. For Y, we do need to add some kind of a noise. Well, it's not going to be able to replicate it anyways. Okay. Model input IDs. Wait, in our models we just say loss, get loss, get lost, get loss. Okay. So these are the models. Forward, if loss is not none, value tag is this thing, which means in all these cases we don't need to do the maxlen plus 1 thing. It automatically gives us the maxlen sequence. We just need to use loss is equal to true flag, y.shape. Huh? How is it 0? Oh, better. And we still do up to n and this up to n. We do x.shape. If I do this and I do data.shape, look at 10. Yeah. If I do this, what is the shapes I get then? Alright, perfect. So the models are now completely consistent. Dataset creation is completely consistent now. Now what you're going to do is, how is this going? So it's going to be following the same loss value, learning the trajectory till it goes to the top. Okay, and if I do input IDs is equal to this model takes both the values and value targets and losses equal to none. Yeah, so the input IDs become torch dot tensor x no, yeah, x what is x? Let's just print x for convenience. Yeah, this is x dot long. Value targets is y torch dot tensor y dot, no, not long, loss is equal to true. Alright, so it's not working. Why is it not working? I can just copy this function right here and we can just call it from here. F is not defined. Okay, why is that? So first print x base model attention x dot last hidden state so the input IDs, oh my god, ah, cool. Tensor x x range out of self cap plus 1. Okay, it's not working. We remove this thing, which is the x dot last hidden states, and it returns us these values. Alright, cool. So you can see the loss value is pretty low, while the policy so the loss value is pretty low and the policy value is this thing. Now what you're going to do is we're going to ask it a couple of things, which is configure optimizers and init weights. Now when you're going to initialize it, we also need the training configuration, so we're going to use this. Let's not use that. Scheduler is, what is the best scheduler that we have? It is warm-up constant, and we're going to say 14% of this thing. Batch size is equal to 3. And this thing returns x dot shape, y dot shape 11. So it should be, you know what, let's make this 12. If I do x, I do get good sequence, and it is this thing, and that's it. That's good. That's good enough for us. Okay, now what we need to do is we need to define the sweep parameters. The first thing we do is model.apply init weights. Okay. This loss is super low, means that this thing is pretty unusable. Tannage backwards. So because you're initializing the weights with because of the normalization kind of thing, where you have values, so the weights get initialized with mean 0 and standard deviation 0.02. That's why you're getting the tannage values so close to 0. They should be fixed. The loss is super low. Oh my god. I think we messed up. The y that we're getting is already very, very small. Let's just make it. Now it's not better. Now this value is going to be scaled between we need to scale this thing between -1 and 1. So we first multiply this, get negative values. Do we get negative values? My god, what am I doing? We have to apply it to this thing. So this thing is now pretty much fixed. This thing minus we do to n and y up to n. So what we have to do is we add by 0.5, divide by 2, and no, plus 2 minus 0.25 times 2. Yeah, now we're getting some good values. Times 4. Then you start getting values between -1 and 1. Okay, perfect. So we need to also apply this kind of a normalization here, so we can get some good values out here. Okay, perfect. So you see the values are pretty close to 0. That is because the okay, so this is something that also might be happening in this model, that the values that it is predicting are very close to 0, whereas the actual values can vary between 1 and -1, as you can see the case here. Now what we need to do is, wait, how can values go above 1.4? 1.29. 40 times 2. Well, let's just keep it at this value. 0.114. This makes much more sense now. Perfect. Now what we need to do is we need to configure a particular optimizer. So we're going to say optim is equal to configure optimizers model trainer conf, and yeah, I'm going to say weight decay, which is I think initialized by default. Yeah. Optim. Perfect. Now what we're going to do is we're going to see that this particular value for I in range 4. We run this thing and loss dot backward, and we say optim dot backward. And what we are going to do is we are also going to log what is what are these values. Create dataset. Perfect. RMW object. Oh, sorry. Step. And my laptop is going to start yelling. So the values are decreasing. I mean, it's inevitable, man. Values are going to decrease anyways. So what you're going to do is we're going to convert this thing to a T range. So you have P bar is equal to this t range for I in p bar, and p bar dot set description f loss I comma loss up to 0.3 floats. Okay, and we're going to import this thing from tqdm import t range. Perfect, you beautiful thing. Try to 180. Oh, and we should probably log the individual values for reference. It's gonna be loss policy dot point 3f and loss value dot point 3f, and let it be 40. Yeah, so we're seeing that it's not actually reducing by a lot, which we would like to see it reduced by a lot. Okay, so now num layer should probably be 2, because you need to have at least one body. Yeah. Yeah, this value is not going down by a lot. So what we're going to do now is, we have all these things set up. We do have the dataset creation, we have the training piece, and now we are going to use WNP sweep basically. Now let's see. Yeah, so this thing, yeah, you see it's almost the same function once you zoom out. And it's going to behave the same trajectory here. Now what the difference that we're going to start seeing comes from here, which will be in approximately another 1 hour, another 40 minutes. So this is at epoch 2500, we are at 1000, so 2.5 times that thing, which is 30 more minutes, which makes it 50 minutes. 50 minutes, but during that time you're going to see 2 more 10 batches, so yeah, 1 hour. In exactly 1 hour we are going to see what happens here. Till then, let's continue with exploring WNP. WNP. But let's do it here. Overview. Projects. Create a new project. This is sweep practice, I guess. Public project, I don't want to hide anything. Open project, let anybody contribute here. Okay, my god, man, people are going to steal my tokens. And what you're going to do is you're going to run this function. Oh, perfect. So now we need to create a simple script for running this thing. Probably should upgrade wnb pip3 install wnb dash dash wnb dash dash upgrade. Right, so we create a Testbench script. I'm going to call this testbench.py. Okay, and I'm going to create this thing, wnb. Now we need to import a lot of this stuff, so we're going to call this thing. I'll create this thing. We'll also need to include these things, which is set seed. Every time we run this thing, we are going to set seed to 4. We are going to fix this thing, add some value, and finally import other packages. Okay people, cool. This is an absolutely horrible, this is an absolutely horrible piece of code, but who gives a shit? Now going to define this thing, config, and secondly we are going to define our create loop thing, the training loop, let's just call it. And that's it. That's all we need. Now what else do we need to do? Yeah, wnb log loss, let's just do that, and we don't need to save this thing. Now what we need to do is we need to run this code. Python testbench.py, invalid syntax. What is invalid syntax? Okay, clearly we fucked up somewhere. What? Module name W and B? Oh, Python 3. God damn it. This is right. WNB online. Now this thing, the entire shit will be synced to the cloud, and yeah, Let's just run one cycle and see what happens. Name error X is not defined. Delete run. Yeah, man, we don't save shit. People are going to steal my tokens. Have nan loss, man. There is no data. Loss is nan. Why is that? Let's just instead of actually importing the code, let's just write our own code for the model. Oh. Let's just do 10 for now for debugging. What's the issue? What's happening here? This does not happen if I do it here. Yeah, and why here? Okay, so torch.tensor x long and torch.tensor y, and we print x and y. Oh wait, there should be c is equal to true. Okay, cool. Now it's working. Now it's working. Okay, so what we're going to do is we are going to we're going to run a sweeps now. Delete run, and finally delete run. Okay, now what we need to do is, I need it to run at least one. No worries. Going to run this thing. Takes 10 seconds to actually run. Alright. Cool, man, cool. So this page is now ready. Right, sweeps practice. I do this, and now I'm going to see what was my loss. I had a beautiful loss curve. Now we're going to do sweeps, people. First is C docs. I did try to do something for the cloud. I don't know how sweeps works though. add WNP, write config. Biggest strategy, we support grid, random Bayesian search as well as early stopping. Check out some example configs here. Initialize sweep. Launch the sweep server. We host a central controller and coordinate between the agents that execute the sweep. See, train.py, and it needs to default. It needs a default dictionary. Config is equal to defaults. Okay, so let's not put it here. What we are going to do is we are going to call it right here, and for config has a dictionary. Config is supposed to be a dictionary that takes in scheduler, warm-up constant, and it takes in what is the warm-up percentage, which is 0.14, and it takes in the weight decay value, which is 0.1, right? So let's just put this to 100. It will finish in a second. Okay. Alright, what do I see here? We need to open on the page for this. I can see that there's just one model. What is the name of this model? It is Prime Snow 24. It's not here. Ah, shit. Active. This is sweep practice. Dude, this is sweep practice. Why are you going here? No, boy. Went to the wrong place. You're barking up the wrong tree. Blindfold chess. No, not Prime Snow. Delete this run. Yeah. Oh, it's also logging the test accuracy now. Oh, that's better. Much better. No. You, sir, are supposed to let's just initialize it here for safety, and what you're going to do is you're simply going to pass it the config object here. What happens now? Yeah, so it's going to the sweep practice now. Much better. Alright, so I go to sweep practice and now I see stoic garage. Perfect. We're going to delete this, and we're always going to run these things for 500 epochs. Yeah, 500 epochs is good enough. And then what we're going to do is we are going to practice sweeps. What exactly is sweep? Alright. So I go to sweep. I need to create a sweep. Now I've already studied a little bit of what this is supposed to do. So I have parameters, and then each parameter is basically the name of the parameter is scheduler, and it has values that are warm-up constant, Then the other value I have is norm decay, norm decay, cosine decay. Yeah, these two are good enough. And the other I have is warm-up percentage. Values are I did study one case where hyperopt.yaml hyperband.yaml, where you can just define what is your minimum and maximum, and it would figure it out by itself. But you know what, let it be. Values are 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and the final value we have is weight decay, and it also has the values, the same values. Initialize sweep. Okay, so it is supposed to take train.py 81. I also need to configure what script works best. So what script I actually need to use. Command line, distributions, parameters, stopping criteria, valors, Python 3 extra parameters, use with hydro, common questions. What does it say? This week. Oh, program is not train.py, it's testbench.py. And what we need to do is we need to add arg parser. From arg parse import arg parser args is equal to argument parser args dot add. We need to add two things to this thing: weight decay, warm-up percentage, and scheduler. Delete sweep, add argument dash dash scheduler, type is equal to str equals args is equal to args dot parse args, and the other value is going to be weight decay and warm-up percentage. Type float. Yeah, I think this is smart enough now, and we need to pass it this thing, args.scheduler. Perfect. Now we need to create a sweep, which is program testbench.py. Warm percentage, maximum is this, minimum is this, distribution is uniform, and the possible values you have is cosine decay, norm decay, and warm constant. Distribution categorical. Minimize. Or what do we log? We log capital loss. Okay. Initialize sweep and copy this, paste it. Let's see. In Python, this has to be Control C. Okay, so I need to add the flag which tells me what is the environment. Command line command -env. Let me go back to the sweep. Can you show me what is? No. Well, fuck you too. This is really neat though, you know. I like this. Delete sweep. Create sweep. Command. So what this does is it runs command this /user /bin /env Python 3 Python 3 weight decay maximum is 0.8, minimum is 0.0, warm up percentage maximum is 1.0. This is this command Python 3 testbench.py scheduler this, warm up percentage this. Okay. Ah, shit. It just just started Python 3 environment interpreter. Trying to go back to apply to delete the sweep. Okay, delete. Just a minute, people. Command / does that actually work? /usr /bins /python Now env python 3. Smart. So what we need to do is the command is going to be this thing, and then you have to run python 3, and then file will be no, configuration categorical sweep agents construct a command line in the following format. Here, let's start with this value. Oh, all I need to do is this then. Now it makes much more sense. Let me save this. Initialize sweep, and now we're going to see some magic. Starting WNB agent. Shit. Still using train.py. We went wrong. Where did we go wrong? Kill this thing, delete the sweep. Man, this is tired. This is a tiring work. Testbench.py. Metric parameters. Weight decay 0.9. Initialize sweep. Now people, now it is going to work. Please work. Anyway. I've never done hyperparameter optimization. I should probably study a little bit more about it. Oh, see? Nice. Now it's going to use a warm-up constant, and it is using weight decay as 0.10. Super sweep 3, unsweep, dandy sweep 4, warm decay, warm percentage 0.0922. This is neat. This is actually very good. Anyways, where did we go? Blindfold chess. Yes. Another 20-30 minutes and we'll be reaching that mark. Now it's doing all this to actually it's iterating over all these parameters, which is what category to use. So using cosine decay, having a small weight decay is good. Okay. I don't understand any of it. Man, oh man. Parameter importance. I think this is going to come once the piece is done. You know what I'm going to do is, I think once this thing is done, I'm going to stop the stream and I'm going to let this model run, and I'll update you on the next stream of what happens. See, it's doing so many runs. It's not possible for me to do so many runs on this system, because you see, it's taking like, oh my god, it's too many steps. But yeah, the good thing is that using this way we have created, so I'll just open up my task list. What we discussed we'll do is, yeah, so we have already done this piece, which is good, but the problem now is that it's taking too long to do all these sweeps. How do I configure it? Search strategies, stopping, we support the following. Hyperparameter stopping evaluates whether program should be stopped or permitted to continue at one or more brackets during the execution of program. Brackets are configured as static iterations for a specified metric, where the iteration is the number of times the metric has been logged. If a metric is logged every epoch, then there are epoch iterations. Hyperband max iter 27. This thing is just keeps on spinning. It is interesting though. Okay, you know what? I'm going to terminate this program, and we're going to refresh this page and see if there are some advantages. What is it? Importance, weight decay, correlation 1, weight decay. So if you have, basically, it's very clear, the lower the weight decay, the more it's learning. But that's not the true with, oh wait, Okay, scheduler value cosine norm. You know what? That's it. That's it for stream. Yeah. Now I do need to figure out how we can utilize this. How we can utilize sweeps with our blindfold chess AI algorithm, because I would like to see, because you see, I don't want to do too many experiments. See, it did like 18 runs in 5-10 minutes, but this thing takes a lot of time. Probably understand the stopping criteria a little bit better. Specify the stopping algorithm. Yep, that's it, people. That's it for today's stream. We're going to do a lot of work. I'll probably record another stream later at night or tomorrow. Who knows? God knows. Okay then, bye bye.